So hi everyone. I suppose you all know Joshua. Joshua Leos. Joshua has been here since he started his PhD in 2016, right? He did his master's in robotics, then he joined the lab and did PhD. So his project has been very unique. So a little bit different from the rest of the lab that just creates more challenges for the student who does that. And moreover, he started working with someone very unique, Dr. Gordon, who decided to open up his new field, neuroplastic surgery, and Joshua worked on that. So everything was very unique and needed very independent researcher. So Joshua showed during the last few years, I can say that he was a great independent researcher. He could do everything, and you could expect, as he will show here, do everything by himself: software, hardware, software design, system integration. And we're very thankful for all you did, Joshua, regardless of what happens today. So, and so he will talk about the thesis. So again, just I stress that he was so good that we are trying to keep him here and not let him go so fast. Hopefully he stays with us. And so his the title is here, Robotic Implant Modification for Neuroplastic Surgery. And Joshua, take it away.
Okay. Thank you, Dr. Ahmed, for the introduction. And thank you, everyone, for coming today, and for those who are joining through Zoom. And today, I'd like to talk about robotic implant modification for neuroplastic surgery. So to begin with, you may ask, what is neuroplastic surgery? Neuroplastic surgery is a novel special field that combines neurosurgery and plastic reconstructive surgery. Unlike the conventional neurosurgeries, neuroplastic surgery not only provides optimal neurological care and treatment for the patients, but also to restore the patient's preoperative normal appearance. Just before I jump into more details, I'd just like to briefly explain some terminologies that I'll be using in my talk. Craniotomy means creating a resection on the skull to gain access to the area of interest. And then craniectomy is similar like craniotomy when it has to do with the bone itself. For instance, when the tumor is growing onto the bone, or in emergency cases, such as a traumatic injury, the skull bone needs to be removed to relieve the intracranial pressure. Well, both craniotomy and craniectomy has to do with the removal of the skull bone. Cranioplasty aims to repair the skull bone. When the bone flap that's been removed from the patient is still functional, it can be placed back immediately. However, in many cases, as I mentioned, due to trauma, the bone flaps are already damaged, or due to a cancer, the bone is no longer functioning. In such cases, we consider using a patient-specific customized cranial implant that's designed using computer-aided design and manufacturing technique based on the patient's preoperative CT images. Therefore, it matches the exact geometry of the patient's original skull bone. And it can be made of different type of materials, such as PMMA, PEEK, and even titanium alloys. However, the fabrication of such customized implant takes about 2 to 4 weeks. So after the initial surgery, the patient does not have a full skull bone to protect their brain. Therefore, they are at a high risk of a brain injury or infections. Therefore, whenever possible, we only consider single-stage cranioplasty. That is to reconstruct the skull immediately following craniotomy or craniectomy. There are many approaches to achieve single-stage skull reconstruction. One approach is to use the skull resection to create a hole on the skull bone that matches the given prefabricated implant. However, this approach restricts the flexibility during craniotomy, which is not ideal because during neurosurgeries, in many cases, the amount of bone removal needs to be revised due to the surgical need. Other methods consider intraoperative freehand molding. This method generates an ectothermic reaction that can damage the surrounding tissue. And also the patient also may have an allergy to the monomers. And especially for large, complex skull shapes, freehand molding is very challenging. It often results in unacceptable cosmetic outcomes. Therefore, other research groups consider using the removed bone flap to create a mold first and then custom that acrylic PMMA implant. However, this certainly increased the surgical time. And also, as I mentioned, the bone flap that's removed from the patient may not be usable due to damage or it's already cancerous. So people may wonder, with the fast development of 3D printing technology, why can't we just 3D print an implant and put onto the patient? Well, it's very obvious. It's impractical due to its long fabrication time. And also, most 3D printing materials are not biocompatible. To address these challenges, one alternative approach is to perform intraoperative modification of an oversized prefabricated implant. The implant is designed based on the patient's preoperative CT model. Therefore, it matches the exact geometry of the patient's skull bone, but it's designed in an oversized profile to allow intraoperative plan change. So during the single-stage cranioplastic procedure, the plastic surgeon will look at the defect, and then given the oversized implant, he will draw a contour on the oversized implant, and then use a manual surgical cutter to resize the implant to fit the defect. However, this entire procedure is manual. Therefore, it's imprecise and often time-consuming. That can lead to large bone gaps between the skull and implant, and causing implant failure and other post-surgical complications. And to address these challenges, here at Johns Hopkins in 2015, the Big Lab proposed the first computer-assisted single-stage cranioplastic workstation. This system relied on a commercial to perform registration, and the surgeon can use the instrument to trace the defect. And then the projector, there is a projector, can project the oversized implant on top of the oversized implant, and the surgeon can mark the contour on the implant and then perform the resizing. However, there are some drawbacks with this system, such as the bulky setup of the commercial optical tracking system, and also which cannot provide a precise projection, and it requires an implant fixation to be fabricated for each implant. And the third drawback is it requires a reference marker pin that to be attached to the skull bone. Therefore, to address these challenges, I have designed 3 systems: a portable projection mapping device for intraoperative surgical navigation and guidance, and an ultimate workflow using a robotic system to perform implant resizing. And lastly, I will present you a 5-axis laser cutting system for implant resizing. So first, the objectives to have a portable projection mapping device is to provide a surgical navigation, a better AR experience, augmented reality experience than the head-mounted display. Because during the surgical procedures, the surgeons normally already wear a surgical goggles. Therefore, having them wear a head-mounted display will add extra burden to them. And also, head-mounted display requires eye calibration each time, and there is always accuracy issue with it. And also, to get away from using bulky setups such as commercial optical tracking systems, it also suffered from line of sight. To address these challenges, I designed this portable projection mapping device. I combine all the components into one single unit. It consists of a laser projector and a small optical camera, tracking camera that I converted from a Intel RealSense RGBD camera by adding 2 bandpass filter onto the stereo infrared cameras to track surgical instruments. And the picture on the right demonstrates the application of PPMD device in single-stage cranioplastic. After registration, it can project an oversized implant over the defect on top of the skull at the right location. And the surgeon can use the surgical instrument to trace the defect, and then it can project the collected defect onto the skull. And let me now just quickly show you how this system works. First, we need to perform two calibrations. The first is the camera projector calibration. This is to find the extrinsic transformations between the RGB camera and the projector. And this is done by using a calibration board. And we hold the calibration board in front of the camera and to different poses while the camera capturing images. And the projector is projecting a circle dot pattern. And the calibration is based on stereo vision calibration. We are treating the projector as a camera. Therefore, we can compute that transformation between the camera and the projector. And then we need to perform a pivot calibration to configure the surgical instrument that we're going to use. This is to find the two-tip position with respect to the markers, and the user just pivot around the point while the camera tracks the surgical instruments. After this two calibration, we can start using the system to perform patient-to-CT registration. So here we first load in the preoperative CT model into our GUI, and the user use the surgical instrument to touch the registration points. Here we have certain registration points attached to the skull, but in other cases, one can consider using the anatomic features, such as the bone area around the eye orbit or the front area for registration. And after registration, the camera tracks the head model. We can immediately visualize the patient-to-CT registration by direct projecting on the CT model onto the patient's head. Because we already registered the CT model to the reference marker, which is tracked by the camera. And we also know the transformation between the camera projector from the calibration. Therefore, the CT model now can be rendered in the projector space. And the next, we want to use the surgical instrument to trace the defect contour. And we have developed an optical tracking algorithm to recognize, to detect this instrument. It's by stereo vision triangulation. For each stereo images that's coming in, we first detect the markers, and then we can triangulate their 3D coordinates. When there's no instrument tracked in the system, it goes to detection mode, which will look for instrument models. Once it finds a model, it computes its surgical instrument pose, and they will switch to the tracking mode. The tracking mode is running at a much faster frequency at the frame rate of the camera. In this case, we're using a RealSense camera that can run up to 90 Hertz. And then we evaluated the tracking accuracy of this system by comparing to the commercial optical NDI Polaris trackers. We were using the same digitized probe move freely in space and to record their positions. And this is the results of our tracking system compared to the Polaris. The red is the Polaris system and the blue is our system. As you notice, as the instrument move further away from the camera, and our tracking becomes unstable. This is due to the fact that the baseline between the stereo cameras are very short. Therefore, our device is mainly for short-range applications. And this video demonstrates the application of such a PPMD device in single-stage cranioplasty. After patient-to-CT registration, the device is tracking the head model and is able to project an oversized implant in blue at the right location on top of the defect. And the surgeon can use the surgical instrument to trace the defect contour while the camera is recording the position of the two tip of the instrument. And then we can immediately visualize the collected defect contour. To conclude this work, we have proposed a portable projection mapping device to provide surgical navigation and visualization based on projector-based augmented reality. And we developed an open source optical tracking algorithm to track multiple surgical instruments in real time. And we investigated the system's tracking accuracy. And we also demonstrate the device application in single-stage cranioplasty. With this system, is able to provide a surgical navigation and guidance for neuroplastic surgeon to perform a better single-stage cranioplasty. However, as you may notice, the implant resizing is still a manual process. Therefore, it's imprecise. And also, it requires the user to hold the surgical instrument to trace the defect, which can also be imprecise. And it's also the projector requires a good dimmed lighting environment, which may not be the case in the surgical room because the surgical light. And also, it still requires a marker pin attached on the skull. However, the concept of the portal projection mapping device enabled us to further automate the whole workflow. Therefore, I come up with a new system using a robotic system and a 3D scanner to perform intraoperative implant modification. First, we use the 3D scanner to scan the defect model, and then we register that scanned defect model to the CT model. And then we can use the defect information to generate a cutting toolpath on the oversized implant and send it to the robot to resize the implant. The first step is to perform patient-to-CT registration. And this is done by using the anatomic features on the skull. And it can register to the CT space. And once we register the defect model to the CT, we can use the defect model to generate a cutting toolpath. And first, for generating cutting toolpath, we apply a curvature filter to the defect model to filter all the edges around the defect. And then we parameterize all the vertices in a local cylindrical coordinates by fitting a best fit plan through all the vertices. And each vertices can be parameterized by theta and their radius, and their distance to the plan as a function of theta. And then we fit a 3D curve to all the vertices and convert it into a spline curve, which allows user to further adjust if necessary. And then we project this spline curve on top of the oversized implant. And this step also eliminates any registration residual error. And then we use the generated spline curve to generate a cutting toolpath by adding cutting vectors. And here, the cutting vectors are generated based on a constant tilting angle. And once we generate a cutting toolpath, we can send to the robot to resize the implant. But first, the robot has to localize the implant. This is done by first, we'll perform a PV calibration to find the two center points with respect to the robot's end effector. And then the user hand guide the robot passively to contact a minimum of 3 predefined registration points on the implants to localize the implant. And the implant is designed from the CT model. Therefore, once the robot localized the implant, we register the CT space to the robot space, and the cutting toolpath can send to the robot to resize the implant. And we conduct experiments to evaluate our approach with the conventional manual approach and the optical tracking method. We generated six sets of data of oversized implant and the defect at a different location of the skull. And to save printing materials, 3D printing, we only 3D print the partial skull. But to have anatomical features to register this model to CT, we added fiducial points as anatomic points. And for implant localization, there are 3 predefined fiducial markers. However, for implant manufacturers, they normally do not provide implants with customized markers. Here, this video demonstrates side by side the robotic cutting and the manual resizing. The speed it played 8 times faster. As you may notice, the manual resizing, Dr. Gordon has to go back and forth multiple times to try to adjust the implant to fit the defect, whereas the robot just have one clean cut. To evaluate the resizing accuracy, I computed the gap distance between the skull and the resized implant. This is done by first fit the implant to their respective defect models. And then I 3D scan this model. And I can register this model to the CT space. And then I scan each individual resized implant and register to the CT space. And I can extract the contour of the defect and the or resized implant. And I can compute the gaps between them. And here is the results of the maximum gaps by manual method and optical tracking method. And it shows that our approach has the minimal maximum gaps. And this is the results of the mean gap distance and their standard deviation. And this shows that our system improved the resizing accuracy by 56% compared to the manual approach, and 42% compared to the previous optical tracking method. So to conclude this work, we proposed a workflow that used a handheld 3D scanner for intraoperative cranial defect data acquisition. And we used the collected defect geometries to generate a cutting toolpath for the robot to resize the implant. And we developed a robotic system for implant resizing. And the system demonstrated higher resizing accuracy than the manual approach. Excuse me. Now we want to prove if this system can be used for clinical applications. For clinical application, when we want to use this system for clinical application, there are a few challenges, such as surgical draping is required to cover the patient during the procedure. And also, we only perform experiments on plastic skulls. When we're dealing with real patients, there are soft tissues that cause registration errors. And also, the defect, as I mentioned, may not be a constant tilting angle, the beveled edge. And also for the robot, it requires a user to passive the hand guide to touch the implant, to localize the implant, which is slow. Therefore, to further improve this workflow and automate this whole process, I come up with a 2-scan registration method using reattachable fiducial markers. And I further improve the toolpath to consider the defect bevel edge. And I added RGB camera on the robot to perform 3D robotic scanning to automatically localize the implant, which I will explain in more detail in the following slides. So in clinical scenarios, surgical drapes is required to cover the patient's head, only leaving the surgical site visible. It makes it very challenging for us to use 3D scanners to register this model to the CT. Therefore, I come up with a reattachable fiducial markers that can attach on top of the surgical cloth. And also for automatically localize the implant, I added RGB camera on the robot. And now let me just show you the design of the reattachable fiducial markers. It has 2 parts, a top sphere and the bottom part. And in them, there are 2 small magnets that hold them together. And this is a cross-section view. The bottom part can be adhered to the patient's skin. When the patient comes in for the surgery, we attach these reattachable fiducial markers on the patients and perform a first 3D scan. And then after draping and craniotomy, we can reattach these fiducial markers back to their original locations, but on top of the drapes. Then we perform the second 3D scanning. And the second model can be registered to the first head model using these reattachable fiducial markers. And the first model can be registered to the CT model. Therefore, we complete the patient to CT registration. And then we can use the registered defect model to generate a cutting toolpath. And to address the previous constant angle toolpath generation, we now consider the defect edge. We want to generate a cutting vector that's parallel to the defect edges. This is done by fitting a plane along the defect edges. And then we have the tangential vector cross the normal vector. We get a new vector that's parallel to the defect edge and perpendicular to the defect contour. And then we can send this toolpath to the robot to resize the implant. The robot needs to localize the implant. And now we consider using the RGPD camera to perform TSDF fusion to automatically localize the implant. The first step is to calibrate the camera with respect to the robot, also called hand-eye calibration. This is by using a calibration board, and we command the robot to move to different poses where the camera captures the images. And then we can compute the transformation between the camera and the robot NB factor. And once we have this transformation, we can perform robotic 3D scanning. We plan a circular path above the implant fixture platform. And we having the camera to take depth images, and the truncate sine distance fusion function can fuse all the depth images within the bottom. So we can generate a 3D mesh of the physical implant and in the robot space. And this implant can be registered to the CT space. Therefore, the cutting toolpath that we generated now can be transformed to the robot space to resize the implant. And we conducted phantom experiments and cadaver experiments and we used reattachable fiducial markers for registration to address the draping issues. And as you notice, the first scan of the plastic skulls is almost identical to the CT model. Therefore, the registration between these two models is very simple. But this is not the case for cadaver because the soft tissues. As in the next slides, I will show you the cadaver experiments. If you don't like to see cadavers, you can close your eyes. So when the surgical drapes are not required, we only need to perform one 3D scan to get the defect model and the head model. And then we can use the anatomic points to align this two model, and then run the iterated closest points algorithm to register these two models. But in order for ICP to work, we have to have a certain amount of overlapping areas. Therefore, it requires surgeons to open a larger scalp to expose the scalp, which is not ideal. And then after registration, we can use the defect model to generate a cutting toolpath on the oversized implant and send to the robot to resize the implant. But in most cases, surgical drapes is required to cover the patient. And as I introduced, I'll use a two-scan method to register this defect model to the CT space. And by reattaching these markers on top of the drape, the defect model can register to the head model. And the first 3D scan head model can register to the CT model. However, due to the soft tissues, normal ICP will not work. It will end up in a very unrealistic results. To address these issues, I come up with a modified ICP by first scaling the 3D scan head model to the size of the CT model. And then I run the ICP to register them. And then I scale the head model back to its original size with respect to their geometric centers. And once I complete the registration, I can generate a cutting toolpath on the oversized implant and send to the robot to resize the implant. And to evaluate our system, we compare the resizing accuracy with the manual approach. And here you see Dr. Ben Shalom is performing the manual modification of the oversized implant. and try to fit the defect on the skull. As you notice, he has to go back and forth multiple times to adjust and trim the implant to fit the defect. And this video is played by 16 times faster. So it takes a long time, and even with that, the resized implant still has quite large bone gaps. And then I will demonstrate our robotic approach. So by our robotic approach, first I perform a 3D scan on the head model, and then perform the craniotomy, create a resection on the skull. And then I perform the second 3D scan. And then I can register all the models together in the CT space. And then I can use the defect model to generate a cutting toolpath on the oversized implant. And once the robot localizes the implant, it can resize the implant automatically. And here is the result of the resized implant that fitted to the defect. As you may notice here, in this case, there are large bone gaps. This is because this area has much complex skull geometries right above the eye orbit, whereas in other cases, it's more like a planar geometry. And to better visualize the result, and I use the same method to evaluate the gaps between the skull and the resized implant. And here I also computed the surface sun distance on the implant surface. This shows the mean gap distance and the max gap distance of the resized implant fitted to the defect. And our system improved the resizing accuracy compared to the manual approach. And this is the time distribution of each steps. The total robotic resizing takes about 10 to 23 minutes. However, these steps can be done on the side. It will not affect the surgical time. The actual resizing time by the robot is only 3 to 5 minutes, whereas the manual resizing can take 10 to 18 minutes, as reported by the paper. So to conclude this work, we further improve the robotic workflow by proposing a 2-scan method and using reattachable fiducial markers and a modified ICP to address the soft tissue and dripping issue. And we further improve the two-path algorithm to consider the defect bevel edge. And we further automated robotic workflow by using RGBD camera to perform robotic 3D scanning. And then we perform cadaver and phantom cadaver experiments to evaluate our system's resizing accuracy. And the system demonstrated higher resizing accuracy than the manual approach. And however, with the 7-degree freedom KUKA robot, it's still using a mechanical cutter, which can create a lot of noise and dust. And also the cutoff implant edges is very rough. And also the robot workspace is very limited. So I also consider using a laser cutter to cut the implant. However, most commercial laser cutters only provide 2-degree freedom, which can only cut 2D patterns. In order to cut 3D shapes, I have designed a 5-axis laser cutting system by adding one extra translational movement, move motion, and a rotary table. And the overall workflow of the laser system is compatible with the robotic system that I just introduced. The only thing is, since the laser only has 5-degree freedom, we have to consider generating a 5-axis two-path. And this is the design of the system. It consists of different components. It has 3 translational linear stage that provide 3 translational motion, and the rotary table that's holding the implant, that providing 2 rotational motion. And this is the hardware overview of the system. A 100 watts CO2 laser is used, and we also have a distance measuring sensor that can be attached to next to the laser head for registration purposes, which I will introduce in the following slides. And this is the controller overview. There are 5 closed-loop stepper motors, and the laser is controlled by the Gerbil controller. And then I developed a ROS interface to communicate with the controller and the distance sensor. And just to show you how the system works, there are several coordinate systems defined on the system. A machine coordinate system fixed in space, and the workpiece coordinate system where the implant is mounted, and the 2 coordinate system where the laser is cutting. And this is a simplified diagram showing the coordinates transformation. We mount the implant, and then we're given a 2-path that's represented as PN and VN. We want to align the laser to that position and orientation. This is by solving inverse kinematics to solve the joint angles D1, D2, D3, and theta 4, theta 5. First, we want to align the laser to the vector by computing the 2 rotary angles. And theta 5 is the incremental angle as the platform rotates. The capital N is the total number of given cutting locations. And then we compute the theta 4 is the tilting angle. We want to align the platform to that vector. Once we have these 2 angles, we can compute the linear joints by transforming this point P from the workpiece frame to the 2 frame. And then we can solve for D1, D2, D3. And to cut the implant, I have to make PMMA implants. I cannot just cut 3D printed implants. To create PMMA implant, at first 3D printed implant, and I created a mold based on that implant using silicon molding materials. And then I mixed PMMA polymers and monomers to cast into the mold and put in a pressure pot. And after the material cured, I take it out and I get the exact same copy of the original implant, but made of PMMA material. And to localize the implant, I invested 3 approaches. The first is to use the measuring laser to perform a 3D profiling of the implant. However, this approach is not effective. It takes a long time. The second approach is to use the RGBD camera. This is by first perform hand-eye calibration using a Ruko marker and to compute the transformation of the camera with respect to the machine coordinate system. Once we have that, we can use the camera to detect the markers that's defined on the implant. And using this 3D reconstructed coordinates of the markers, we can register to the CT space. However, the implant may not have markers designed from the manufacturers. So I have the third approach is to use the 3D laser scanner by relying on this marker ring. This marker ring has 4 cones. And the tip of the cones can be measured by the distance sensor. And then we mount the implant onto the implant fixture to perform 3D scanning using the 3D laser scanner. And this red circle dots there just for laser scanner to generate the 3D mesh. And once we have the 3D mesh generated, it's in the 3D scanner space. And we want to register to the machine space. We can use these 4 registration points. And once we register to the machine space, we want to bring the CT space to the machine space by registering the implant from the CT space to this model. And in this experiment, we used the same skull model that we used in previous robotic system on the cadavers. And to generate a 5-axis cutting 2-path, we have a rotating plane sweeping the defect. And it's the similar approach, but the constraint for this 5-axis laser cutting 2-path is if the fitted cutting vectors has to be within that rotating plane. And this video demonstrates the the cutting toolpath generation. And once we generate this 5x laser toolpath, we can send it to the system to cut implant. And this demonstrates the laser cutting of the implant. After laser cut the implant, I just easily pop it up. And as you may notice, the cutoff edges by the laser system is much smooth. Then I fitted the resized implant to the defect model. And you can see it almost achieved a perfect fit. Then I used the same approach to evaluate the resized implant by computing the gap distance and the top surface sign distance. And then I compare to the manual approach. So here, Dr. Ben Shalom, first in the clinical scenarios, they will cut a piece of cloth and based on the defect geometry, and place that piece of cloth on top of the oversized implant to mark the contour, and then manually resize the implant. And then this shows the cutting results by the manual approach. As you see, there are still large bone gaps between the skull and the implant is still protruding on the top. Whereas the laser system, the bone gaps is very minimal, and the top surface is almost matches the original skull bone. With such a close fit of implant, I come up with a new implant fixation to replace the original implant fixation method using titanium plates and screws by using a sideways fixation method without using any screws. This is after resizing the implant, I drill holes on the side of the implant and also on the side of the skull bone. And then I inserted this spring pin into the implant that can click onto the skull bone. I install the implant onto the skull, and it provides a very sturdy fixation to protect the. As I mentioned, the 5X laser cutting system can also provide many functions for neuroplastic applications, such as housing a device for deep brain stimulation and shunt, and even targeted drug delivery system. Because we want to make use of the space of the implant to create a slot on the implant. There are generally two types of pockets we want to create. One is a flat dot bottom, the other is the curved bottom. And then I come up with a two-path algorithm to generate the laser milling two-path to resize the implant. So here the laser is milling a flat bottom on the implant to house this neuropaste device for bliss stimulation. To conclude this work, we designed and developed a 5-axis laser cutting system for implant modification. And we developed an open source ROS interface to communicate with the Gerbil controller and the sensors. And also we modified the laser cutting toolpath to generate 5X laser cutting toolpath. And then we investigated 3 approaches to localize the implant. And then with the implant, the resized implant shows that the laser system is able to provide much higher resizing accuracy. And with such high resizing accuracy, I demonstrated the non-screw fixation and also laser milling functions for potential neuroplastic applications. To conclude this dissertation, I have developed 3 systems for intraoperative implant modification: a portable projection mapping device, and a robotic system, and the 5X laser cutting system to provide higher resizing accuracy for resizing implants. And some of the future work includes conducting more experiments on different shapes of skulls and defects, and also to have a better modeling of the laser to modulate the laser power, and also to further expand the system's application for more neuroplastic applications. Of course, this work would not be possible without the help of many people. First, I'd like to thank Dr. Arman for his tremendous help to me. I have learned numerous research skills from him, and also like to thank Dr. Gordon as the pioneer and in this neuroplastic field. His clinical insights really motivated me to dedicate myself to develop robotic systems to improve this procedure. And I also want to thank Dr. Krieger for being on my thesis committee, for dedicating his time reading my thesis. I especially want to thank William Huang, who have closely collaborated with me and contributed to the development of this work. And of course, I want to thank many people, Dr. Taylor, who gave me very good advice during big lab meetings, and Dr. Ben Shalom, who helped me with many experiments, and Dr. Yudakita helped me a lot on the at the LCSR machine shop, and many others, including all the former and current lab members. Just want to thank you for your help and support. But most importantly, I just want to thank my Lord and Savior, Jesus, who gives me life. I want to thank his steadfast love and goodness. I want to thank all the precious brothers and sisters at Worthy Life Baptist Church for caring for me as a family. I especially want to thank my pastors, Pastor Peter Lee, Pastor James Lee, and Pastor James Kim for their love and guidance in my life. Lastly, but certainly not the least, I want to thank my parents who raised me and provided me in every aspect. And I will not be here today without their love and sacrifice. And thank you everyone for coming today. And with that, I'd like to end my talk and take questions.
Thank you.